So next we're going to look at one of my favorite applications of momentum, and it's one of those applications in a situation where using momentum makes things a lot easier than finding accelerations and forces and stuff that using the other type of material that we've been working on. Momentum makes this type of thing a lot easier, and that is when you have things like collisions and different types of interactions and stuff like that, where this is where we can start talking about the conservation of momentum. You've probably heard of the conservation of momentum before, like conservation of mass, conservation of energy. There's also conservation of momentum. And it's a really, really nice way to look at things when things, hit each other or interact with each other in different ways. And it's a really, really simple idea. Basically, the momentum before the situation has to be the same as the momentum afterwards. No matter what happens before and after, the two have to be equal. Now we're going to kind of idealize this a little bit because we're going to talk about everything in terms of being an elastic interaction. And when we have elastic interactions, then there's no loss of momentum or energy. Now this is kind of unrealistic, but it's a great way to estimate things. There's also inelastic, which of course is more realistic, where energy is lost to things like heat and sound and distortion, that type of stuff. But we're just going to strictly work with elastic type situations because we're just looking for a general idea what's going on. Elastic simulations, or things are close to being elastic, things like when you have like curling or play billiards or something like that, when the curling rocks hit each other or billiard balls hit each other, those interactions and collisions are pretty elastic, but still you can hear the actual collision, which means you're losing energy to sound and a whole bunch of other stuff. But that's okay. We're not going to worry about the reality of inelastic type situations. We'll just work with elastic stuff and just keep it nice and simple. So we're going to take a really, really common scenario, something really, really simple to start off with. It's nothing too crazy or weird. We're just going to start with, I'm going to draw a little line here, and I'm going to bring in a couple of cars. So we have a car right here. All right, so there's a car right there. We'll bring in another car, something like this. Okay, so momentum is a really common thing used to analyze actually like car collisions and stuff like that, and you can sort of try and figure out what actually happened. Okay, so let's get some values going here. Let's say we have a 1,500 kilogram car. Maybe it's traveling at, let's just go 10 meters per second. And here we have a 1,200 kilogram car, and let's just say it's at rest. And the red car here is going to hit the blue car, and we're going to make this nice and simple, but we're going to say that the red car stops after it hits, and then the blue car obviously is going to move forward. So this car right here is going to hit, and it's going to stop afterwards. All right, so we're going to use conservation momentum to find out how fast the blue car is going afterwards. Now, we're just going to use momentums. Now, let's just start nice and simple. I'll start with the red car. The red car has momentum, so obviously if I do P equals mv for this car right here, I've got the mass of 1,500, I've got the 10, I just have to multiply them. We've got 15,000 kilogram meters per second of momentum. And the blue car to start off with, it's got 0. So my total momentum altogether is 15,000. And if that's what I have before the situation, that's what I must have after the situation. So I know that my total momentum is going to be 15,000 no matter what. So if I look at after the collision, if I look at afterwards, the red car stops. Okay, so I know the momentum afterwards for the red car is going to be 0. So all of the momentum must have gone to the blue car. So this blue car must now have all 15,000 for the momentum. So if that car has 15,000 for momentum, I can easily find out how fast it's going. Its V would be its momentum divided by its mass. So that would be the 15,000 divided by the mass of the car, which is 1,200. And if we do the 15,000 and we divide it by the 1,200, it's a lighter car, so you know it has to be going faster than the red car was. it would go off at about 12.5 meters per second, and that's it. So this is a lot easier. You could use acceleration of this car. You need to know the time, how long it took for it to stop. Use that to find the accelerations. Once you have the accelerations, you could find the force using Newton's third law of one force always being in pairs. Apply that force to this car, find its acceleration, find its change in v. It just gets really, really complicated. This is one of those dynamic situations in which it makes it so much easier just to use momentum. So let's take the exact same situation, the exact same scenario. Let's just change it a little bit and go again. Okay, so I'm going to get rid of this stuff down here. Get rid of that. And we are going to adjust this a little bit. So I'm going to get rid of that right there. So instead of this car being at rest, I'm going to say this car is going 5 meters per second. So still a rear end situation. The red car is still going to hit the blue car. And afterwards, instead of this car stopping, okay, let's say it's going 2 meters per second after. Okay, all right, and now let's do the same type of thing with finding the speed of the blue car afterwards. Now I'm going to start the exact same way I did before. Now what I often like to do is I like to look at my before and I like to look at my after. So I'm going to look at my before for my red car. So my before for my red car has momentum, P equals mv, and if I do the mass times the v, which is 10, that's what we're starting out with, it's got 15,000 kilogram meters per second. I'm going to do the same thing for my blue car for before, P equals mv, its mass is 1200, the v is 5, so if I put those two together, it's got 6,000 for momentum. So those are my before momentums. So now what I'm going to do is I'm going to put them together. I want my total momentum before. Now the momentum for the red car is going forward. The momentum for my blue car is going forward. They're going in the same direction. So I put them together. My total momentum is going to be 21,000 towards the right, and that can't change. So that's how much momentum I have to have afterwards. So now let's go afterwards. So I don't know what's happening with the blue car after, but I do know the red car. Afterwards, the red car is still going 2. So I'm going to find its after momentum. Now it's really, really common when you have the same type of, or the same object before and after. It's often common to prime values. This would be momentum before. Prime sort of means momentum afterwards. Same with, this is the first V and this is the changed V. Some people use primes, some people use 1s and 2s, some people do like B for before, A for after. There's lots of different ways that you can do it. Anyway, so I've got the mass, 1,500. The V afterwards is 2. Multiply those together. You've got 3,000 kilogram meters per second. Okay. Momentum for the other car, I don't know. I don't know what that one is right there. But I do know that my total has to be 21,000. Okay. Well, if my total has to be 21,000, and the red car's got 3,000 towards the right, the blue car must have the rest. So if I sort of figure it out, 21,000 in total, I got 3 grand so far. If I just subtract the 2, I've got 18,000 for the blue car. So I have to have 21,000 in total. I know the red car's got 3,000, so the blue car must have the rest, which is 18,000. So they still add up to my 21,000. Well, now that I have the momentum after, and this be momentum primed or momentum blue car after, however you want to label it, I can find out its new V. So the V for the blue car, I'm going to prime it, would just be the 18,000 divided by the 1200. Okay, so we've got the 18,000 as its new momentum. We'll divide that by the mass of the car, and it is going about 15 meters per second towards the right. Okay, so it's pretty simple. It looks like a lot of stuff, but it's not. It's about before equals after. So find before momentums, get the total, find after momentums. Whatever you're missing has to be the momentum of the other vehicle. Okay, so let's change the situation again one more time and see how we can alter it a little bit. Let's get rid of all this stuff down here. Let's get rid of that. Okay, so instead of this guy going this way, let's see if we can take this car and we are going to flip it around. We're going to have a head-on collision instead. Okay, so we have a head-on collision. The two cars are going to collide. So we're going to have these two cars are going to collide together. They're going to collide, and they're going to sort of like stick together. It often happens with cars. Now, obviously, the red car is going to win. It's heavier, it's faster, it's going to win this, but that's okay. We're sort of piece things together, and we're going to do the exact same thing we did before. Before equals after. So let's just find the before. So if we look at before stuff, I can find the momentum of the red car, which is just mv. I got the mass, I got the v, that hasn't changed, so that's going to be 15,000 for its momentum. I'm going to do the same type thing for the blue car. P equals mv. That times that, we got 6,000 kilogram meters per second. Now the only difference here, or key difference, this one's going this way, and this one's going this way. So instead of adding them, I'm going to subtract them because they are vector quantities. So my total momentum has to be 9,000 kilogram meters per second towards the right. 15 grand to the right, take away 6 grand to the left, leaves me with 9,000. So that's the momentum I have to end with. So now let's look at the afterwards. So afterwards, since the cars actually collide, and since they stick together, instead of having two objects, they're stuck together, they actually become one object. So this one object is going to have all of the momentum together. So if I want to find out the v afterwards, I need the total momentum divided by the mass. Now, which mass am I going to use? Well, since they are stuck together, they actually become one mass. So it will be the total mass of the two put together. So I got 9,000. If I put the two together, I've got 2,700 kilograms altogether. And if we take that 9,000 for the total momentum, and we divide that by the 2,700 for the total mass, we're going to get a v of around 3.3 meters per second. And since the total momentum was to the right, the final velocity would also be towards the right. Okay, so it's still the same idea as before. You find the momentums, you put them together, get that total momentum, it can't change. And since we had a different direction, one was going to the right, one was going to the left, we just subtracted instead of added because it is a vector quantity. And since they stuck together, they became one mass. So instead of dividing by individual masses, we can divide by the total mass and find how fast it's going. Again, you can do this with F equals ma and VAT and all those types of formulas, but it is a lot more difficult and a lot more complicated than using just basic momentum ideas. The conservation momentum is a fantastic dynamics tool for any type of collision type situation.